Hello everyone, welcome to Math Enthusiast channel. And for today's video, we will be solving this integral inspired by Asmat Kateya from Romanian Mathematical Magazine in Facebook page. So, uh, in order to solve this problem, we will use the fact that from Euler's formula, we have a nice representation of trigonometric identity, which is sine theta is equal to I times e raised to negative I theta minus e raised to I times theta over 2, and this is due to Euler's formula. So by using this fact to this integral, so we will just let this integral be equal to I. So this integral is equal to I over 2 times integral from 0 to pi over 2 times we will just replace theta here as ln of tan x. So we now have e raised to negative I times ln of tan x minus e raised to I times natural log of tan x divided by natural log of tan x dx. So we know that from basic algebra we have e raised to ln of x is equal to x. So basically the exponent and the base will just cancel, and this will give us only x. So using this to this expression, then we have I is equal to I divided by 2 times integral from 0 to pi over 2 times tangent x raised to negative I minus tangent x raised to I divided by natural log of tangent x dx. So by symmetric property, then we could also say that this integral is also equal to I times I times 0 to pi over 4 of tangent x raised to negative I minus tangent x raised to positive I over natural log of tan x dx. So by little bit substitution here, we will let tan x let tan x be equal to z, then dx here will give us dz over z squared plus 1. So now we have our I is equal to I times I here is equal to square root of negative 1. So this is the value of I here, or basically the imaginary number. So our limit will become um, from 0 to 1, since tangent of pi over 4 is equal to 1 and tangent of 0 is just equal to 0 also. And we will just replace tangent x here as z variable. So this is now equal to z raised to I minus z raised to I, sorry, this is negative, raised to negative I, and for denominator, sorry, denominator, we have ln of z, this is ln z times z squared plus 1 dz. So we will evaluate this integral by considering a function, so such that this function is consider a function f of alpha is equal to I times integral from 0 to 1 of z raised to negative alpha minus z raised to alpha over ln of z times z squared plus 1 dz. So by little bit substitution again here, we will let z squared, z squared be z. Then we will have our f of alpha is equal to I times integral from 0 to 1 of z raised to negative alpha divided by 2 minus z raised to alpha divided by 2 over natural log of z times z plus 1 times square root of z. dz. So by differentiating both sides according to Leibniz rule, we can differentiate both sides with respect to alpha variable. So differentiating under the integral sign will be done according to Leibniz rule. So if we differentiate this, our integral will become f prime of alpha is equal to negative I over 2 times integral from 0 to 1 of z raised to alpha plus 1 divided by 2 plus z raised to alpha minus 1 divided by 2 over z plus 1 dz. So now notice that we can use the so-called beta function. So beta function is given as beta function. So according to beta function, we have gamma of alpha times gamma of beta over gamma of alpha plus beta is equal to integral from 0 to 1 times z raised to alpha minus 1 plus z raised to beta minus 1 over z plus 1 raised to alpha plus beta dz. So using this formula obtained from beta function, so we can now evaluate this integral. So this integral will give us an answer of f prime of alpha is equal to negative I divided by 2 times gamma of 1 minus alpha plus 1 divided by 2 times gamma of 1 plus alpha minus 1 divided by 2, and simplifying we will get negative I over 2 times gamma of 1 minus alpha over 2 times gamma of 1 minus alpha over 2. And to simplify these gamma functions, we will use also the so-called Euler's formula. So according to Euler's reflection formula, we have gamma of z times gamma of 1 minus z is equal to pi cosecant pi times z. So by simplifying these two gamma functions by using this Euler's reflection formula, then we now have our f prime of alpha is equal to negative I times pi over 2 times sine of pi minus pi times alpha divided by 2, and this is also equal to negative I times pi over 2 times cosine pi times alpha divided by 2. So now by taking the antiderivative of this function f prime of alpha, then we will have f of alpha is equal to integral negative I times pi over 2 times integral of 1 over cosine pi times alpha divided by 2 d alpha, and this is equal to negative I times natural log of tangent pi times alpha plus pi over 4 plus c, where c is an arbitrary constant. So notice from the beginning that if we take the let's say limit as alpha approaches to 0 of f of alpha, then it is also the same as saying getting the limit as alpha approaches to 0 of integral I times integral from 0 to 1 of z raised to negative alpha minus z raised to alpha over ln z times z squared plus 1 dz is equal to 0. So by using this, then we can now get the value of this arbitrary constant. So now we have limit as alpha approaches to 0 of negative I times ln of tangent pi times alpha plus pi over 4 plus c, then taking the limit of this expression will give us 0. So we now have 0. So there we will get the value of this arbitrary constant if we evaluate this limit. Then this will give us our c is equal to 0. So now we have our f of alpha is equal to negative I times ln of tangent times pi alpha plus pi over 4, and our aim here from the beginning is f of I. Then f of I will give us this I times integral from 0 to 1 of z raised to negative I minus z raised to I over ln z times z squared plus 1 dz is equal to negative I times ln of tangent I times pi plus pi over 4, and this is nothing but equal to arctan of square root of e raised to pi minus square root of e raised to negative pi over 2. And this is our final answer to the problem. So if you like this video, please consider subscribing to my channel, and don't forget to click the ring button so that you will be notified whenever I post new content. So thank you and God bless you all.